Jnanam Paramam Dhyayam. Knowledge is supreme.
Welcome to the third lecture of the course Advanced Transition Metal Organometallic Chemistry. The topic that we have been discussing over the past two lectures had been about allyl and enyl ligands and their complexes of transition metals. We had looked in the last class about various preparative methods that are used for preparing these transition metal allyl and enyl complexes. We have also looked at unique features that are prevalent between the interaction that exists between transition metals and allyl and enyl ligands. Of the various synthetic methods that we have discussed about in the last lecture, all of them can be classified into three main subclasses. The first one is more of a salt metathesis type reactions in which metal halide precursors are treated with allyl anion. The second subclass, the examples of which we discussed, belong to conversion of transition metal sigma allyl enyl complexes to transition metal sigma eta 3 type allyl complexes. Our last type that we discussed was about conversion of transition metal olefin or diolefin complexes to their eta 3 bound transition metal allyl complexes. Now, in this discussion, proceeding further, we are going to look at various other preparative methods which are available for making these transition metal allyl and enyl complexes, and this would form the topic of today's lecture. So, starting from where we left about conversion of metal olefin complex to the corresponding transition metal eta 3 allyl type complexes, another example of such reaction involves the reaction between a metal salt and an olefin in presence of base. For example, reaction of disodium PdCl4 with this olefin in presence of sodium carbonate gives the corresponding allyl complex So, this is a dimer of the type this. So, in this, the reaction of a metal palladium tetrachloride dianion with this olefin in presence of base gives this following eta 3 bound allyl ligand. A possible mechanism of this is shown over here. So, first this disodium PdCl4 reacts with the olefin with the elimination of a chloride anion, resulting in this olefin bound PdCl3 species, which is monoanionic in nature. This species further loses another chloride anion as the migration of this hydrogen from olefinic moiety onto palladium, leading to the formation of a palladium hydride complex of the type shown over here, that loses HCl to give this palladium allyl dimer. So, the reaction proceeds in two steps, in which the first chloride is lost, giving a monoanion, and subsequently the second chloride is lost, and further loss of HCl results in this palladium allyl dichloride. Another strategy involves the reaction of metal salt with allyl halide The reaction is given as follows: Na2PdCl4 plus C3H5Cl in presence of CO catalytic amount, H2O, and methanol gives rise to this palladium allyl chloride dimer. This reaction is accelerated by reducing agent like CO. So, in this, one has to note that this is a disproportionation reaction in which this carbocation, where the allyl chloride carbon is positively charged, tends to become allyl anion, and the reducing agent for that species is this CO, whereas palladium remains in +2 state all the way. So, this is an interesting reaction whereby palladium allyl chloride dimer can be formed. This palladium allyl chloride dimer can also be directly obtained by the reaction of the palladium allyl chloride with palladium 0 species simply by following the oxidative addition route. There is another example in which one observes the conversion of eta 2 bound allyl alcohol to an eta 3 bound allyl complex. The reaction is shown over here. In particular, the reaction of Cp manganese CO olefin CH2OH when reacted with protonating agent like HBF4 actually protonates this alcohol and eliminates water, resulting in the formation of eta 3 bound allyl manganese complex. So, this is again a 18 valence electron complex, and that arises from 5 of the Cp, 7 manganese 12 plus 3 allyl 15 plus 2 CO4 electrons, that means 19, and since this is a cationic complex, so overall this is a 18 valence electron complex, which means that it is both coordinatively as well as electronically saturated. Along the same line, formation of eta 3 allyl complex can also be observed by simple electrophilic addition to an activated diolefinic complex. This is a very interesting reaction, and this is seen as an electrophilic attack on an activated diolefinic complex. This is specifically given as the reaction of this diolefin complex of iridium bound to a Cp ligand, which when treated with a proton in presence of coordinating ligands like carbon monoxide results in protonation of one of the olefinic bond, giving rise to the formation of a methyl moiety like this or this, alongside the formation of a allyl eta 3 bound allyl ligand. Similar to what we had seen in case of manganese, the previous example, this one also is a 18 valence electron complex and can be seen from the electron counting as follows: 3 for the allyl, 9 for the iridium 12, and 2 gives 14 and 5 19, having a overall cationic charge which makes it 18 valence electron. So, the important strategy that has been used is that the coordinative unsaturation or the vacant space created by the protonation of the diolefin resulting in eta 3 allele is then filled by a Lewis base or donor ligand like carbon monoxide. Caused by the protonation is filled by a Lewis base. We have observed in the course of this discussion about various ways of making these eta 3 bound allyl transition metal complexes. We had observed that these can be formed from the olefin complexes or diolefin complexes by electrophilic additions, the way we had seen the example in our previous discussion. Now, we are going to take another example where it will be a nucleophilic addition to an activated diolefinic complex. So, this is exactly opposite to what we had discussed in our previous example, where a diolefin complex was in fact protonated, resulting in the eta 3 bound transition metal complex, and in this case we will see the opposite. We will see the diolefinic complex of transition metal being attacked by a nucleophile, resulting in again the same eta 3 bound transition metal allyl complex. So, this is a very interesting reaction from that perspective, and sort of encaches on the Umpoling reactivity of olefins when they bind to transition metals. So, here we have a molybdenum complex bound to a diphenyl as is shown. This also is a eta 4 bound diolefin complex and also is a 18 valence electron compound. 5 plus 6 11, 11 plus 4 15 plus 4 19, having a cationic charge. So, overall that makes it to a 18 valence electron compound, and it is eta 4 bound or diolefin complex of molybdenum that when treated with a nucleophile results in attack of the nucleophile on this diolefin, yielding eta 3 bound allyl complex as is shown over here. Now, this has become a eta 3 bound allyl complex. Again, it is a 18 valence electron compound, 5 plus 6 11 plus 3 14 and 2 carbonyls plus 4 18. And what we see that this attack of nucleophile anion onto this cationic molybdenum diolefin complex results in the formation of this neutral compound having eta 3 allele bound to this molybdenum. Now, there are two interesting aspects of this particular reaction. One is this Umpulang reactivity of this diolefin. Usually, free olefins are extremely electron rich and they do not get attacked by another electron rich entity like the nucleophiles or carbanions. Now, these free olefins, when they get bound to the metal, particularly they get activated, particularly when they are in a cationic metal complex, they are even further activated, which can facilitate the attack of this carbanion onto the olefin, resulting in the exhibition of this Umpulang reactivity that is so famously called, and that attack happens at the olefinic carbon with the addition of the R group at the terminal carbon, resulting in the formation, simultaneous formation of eta 3 allele ligand. So, here is another very interesting example in which the nucleophilic addition to a diolefin complex has been discussed, and this reaction as well as the earlier one reaction where electrophile addition to the diolefinic complex was discussed, these two reactions together fall in the third subcategory of the methods which are available for preparation of this transition metal eta 3 allyl complex, and this third category involved the class of reactions which converts diolefin complex onto their eta 3 allyl counterparts by the addition of various electrophiles and nucleophiles. Next comes another interesting reaction, and this reaction makes use of too much electron density present in a metal, resulting in their instability, which if used or exploited in a very clever manner, one can lead to the formation of this eta 3 allyl transition metal complex. So, the reaction or this particular example is titled as hydrogenation of an electron excess or electron rich complex. Let us take a look at this complex. This electron rich or electron access complex is none other than sandwich or nickelocene or sandwich complex of nickel having 2 cyclopentadienyl ligand. Now, the electron richness of or electron excessness of this nickel-leucine complex is very much evident by counting the valence electron of this nickel complex, which is 20 valence electron compound, because 10 5 each from 2 cyclopentadienyl anions and nickel having 10 d10 valence electrons. So, overall that makes a 20 valence electron complex, which sort of is not very stable or relatively more unstable as compared to the 18 valence electron compound, and hence also this nickelocene is much more electron rich, having 20 valence electron as opposed to the more inert or more stable 18 valence electron configuration of other transition metal complexes. So, the treatment of these nickelocene in presence of sodium mercury and ethanol results in hydrogenation of one of the cyclopentadienyl ring along with the simultaneous formation of a sandwich complex of nickel, which contains one cyclopentadienyl ring being inert and the other cyclopentadienyl ring converted to eta 3 allyl ligand having been hydrogenated on the ring carbons. So, overall this complex ends up being a 18 valence electron species. So, 18 can come from 5 nickel, 5 cyclopentadienyl, 10 nickel, 15 plus 3 the allyl ligands, becoming an 18 valence electron compound. And the source of hydrogen for this hydrogenation arise from this ethanol and sodium mercury amalgam, which results in formation of sodium ethoxide along with the generation of the hydrogen. This hydrogen then further hydrogenates this electron excess nickelosine compound and cleverly makes this eta 3 cyclopentadienyl nickel sandwich compound as is shown over here. Another very interesting reaction involved dimerization of allenes. Now, this is a distinct reaction, and this type of reaction does not fall into one of the 3 subclasses that we have spoken about, where these diolefins are activated. This is just a direct reaction of Fe2CO9, the dinuclear iron carbonyl with 2 allene moieties resulting in elimination of 3 carbonyl molecules and formation of this dimeric diallyl iron dinuclear compound as is shown over here. So, this is a very elegant way of generating a dinuclear diallyl complex of iron starting from this dinuclear dicarbonyl compound of iron, and that involves the dimerization of the allene moiety. So, with this I would conclude today's discussion on various preparative methods that are available out there for preparing these very important eta 3 bound transition metal allyl complexes. The most of the reaction today that we have discussed fell in the third category, which involved this conversion of activated or metal bound diolefin ligands to the eta 3 transition metal allyl complex, and these conversion of diolefin transition metal allyl ligand can be achieved by reactions with electrophile as well as nucleophile on the activated diolefin compound to give the product of eta 3 transition metal allyl compounds. Now, we have also seen that apart from these there are 2 other methods. One is that simple hydrogenation of electron rich nickelosine complex in presence of sodium amalgam and ethanol, which resulted in the hydrogenation of part of the cyclopentadienyl ring, resulting in eta 3 bound cyclopentane to eta 3 bound allyl type ligand to nickel, and the Cp ring bound to the nickel, resulting in a sandwich of allyl cyclopentadienyl complex. The other method also was quite distinct in the sense that involved the formation of dinuclear allyl eta 3 bound iron carbonyl complex which was achieved by direct reactions of two equivalent of allene in presence of di-iron Fe2CO9, resulting in elimination of 3 molecules of carbon monoxide along with the formation of this dinuclear diallyl eta 3 bound iron complex. So, with that I would like to conclude on today's discussion that we were talking about various synthetic methods available for transition metal eta 3 allyl compounds, and then we, in the subsequent lecture we are going to pursue this topic in much more detail, particularly in looking at various kinds of reactivities these transition metal allyl compounds usually show and their the reasons behind exhibiting such reactivity. So, with this again I would like to reiterate my thanks for being patiently listening to this today's lecture, and I look forward to deliver the next lecture on the various reactivity aspects of transition metal allyl and enyl compounds. So, with that, thank you and look forward to being with you in the next lecture.